Bismillahirrahmanirrahim. Assalamu alaikum, dear students. We are now starting second lecture for the week number 2, the course of communication systems. In today's lecture, we'll be discussing how we can represent signals in time domain as well as in frequency domain. In our previous discussion related to modulation and other important concepts in communication systems, we only talked about the time domain representation. However, there is another view to look at the signal, and that view is actually named as spectrum or frequency domain representation. So let me begin the discussion by defining the two perspectives. Firstly, we use two different terms. One is called signal and second term is called spectrum. The word signal generally relates to the function of time. If you recall the discussion we had previously, generally we take the signal as a function of time, so it varies with respect to time, whereas the spectrum, for which the plural spectra is used, the term spectrum refers to the frequency domain representation. If you recall, in our previous lecture we have talked about electromagnetic spectrum, and in defining the electromagnetic spectrum and different bands, we refer to different frequency ranges. So that electromagnetic spectrum is actually represented as a function of frequency. So whenever we have a function of frequency, we call it spectrum, and whenever we have a function of time, so we call it signal. These two are two different views of same thing, you can say. Either we analyze the signal in time domain or we analyze the signal in frequency domain. So there are two analysis domains that we use in communication system. One is called time domain and second is called frequency domain. So in time domain, the independent variable that we use in analysis is time, and for frequency domain the independent variable used is frequency. In our book, the Bruce Carlson book, in the textbook, generally the frequency domain description is represented in terms of frequency, cyclic frequency f. However, sometimes we can represent the spectrum as a function of omega, and these two, they are equivalent views because omega and f, they have very simple relationship that relates with each other, that is equal to omega equal to 2 pi f. So by using this relationship, we can transform any function of f into omega and vice versa. However, we will be focusing on the cyclic frequency f for representing the frequency domain functions or spectrum. So if you look at the electrical signals that we use in any communication systems, these signals are basically time varying quantities, and they are presented in either in form of voltage or current. So whenever we have a signal, so we will be dealing with some time varying voltage or current. So basically any signal that exists physically, it exists in time domain because it has some time domain variations. However, it is possible to represent the signal in frequency domain as well. So we can transform the same signal or we can represent the same signal in frequency domain, where the independent variable is taken as the frequency, and that signal is generally represented as sum of sinusoids. So a signal can be considered as composed of sum of many different sinusoids which exist at various frequencies. So we would have a time domain signal which can be represented in frequency domain with a number of frequencies present in the same signal. In order to further elaborate this concept of frequency domain, let me take a very simple case. So we start our discussion with a simple sinusoidal waveform. Vt is equal to a cos omega naught t plus phi, and I'm sure that you are aware of this type of waveform because it's very commonly used in engineering analysis. In this case, this a is actually the amplitude or peak value of this waveform. Omega naught is the radian frequency, which relates to the cyclic frequency by this relationship. F naught is equal to omega naught upon 2 pi. Phi is the phase angle, so phi represents the phase angle of the signal, and t naught is actually the period, repetition period of this waveform, which is represented as 2 pi upon omega naught, or t naught can be represented as 1 over f naught. So consider this simple sinusoidal function, and you can see that this sinusoidal function is actually a function of time. So if I ask you to plot this signal, I'm using the term signal because I am taking it as a function of time. So if I ask you to plot this signal, so the plot would look somewhat like this. So this curve represents the plot of the signal which I have shown, a cos omega naught t plus phi. This t naught is actually the period. This part actually is represented as the phase angle. The difference here, a cos phi, is actually this point here which corresponds to the phase difference. And you can see that the variations of the signal are present with respect to time. So if we change the time, the signal gets changed. The question is it possible to represent the same signal in frequency domain? So how can we show this sinusoid in frequency domain? So in order to show this sinusoid in frequency domain, of course we would be taking the frequency as an independent variable. So if you think of the signal in terms of frequency, so you would need to observe few things. First thing, you should take that this signal has a constant frequency which is represented here as omega naught. However, as I said, we will be using cyclic frequency, so I would represent it by f naught, and f naught is actually omega naught upon 2 pi, as we have previously discussed. So this signal contains only one frequency, which is f naught here, and at this one frequency we have certain other informations as well. So at the frequency of f naught, the amplitude of the signal is represented as a. So this a is the amplitude of this signal, and at the same frequency f naught, a has this signal, this sinusoid has certain phase as well. So the phase angle is represented by phi. So you can see that this signal has two important pieces of information as function of frequency. One is its amplitude and other is its phase. So in order to make a suitable frequency domain description or suitable frequency domain representation, we need to make two different plots, because we have two different pieces of information. First plot would be an amplitude plot versus frequency. So independent variable would be frequency, and the dependent variable is taken as the amplitude. And if we plot it, you would see that we have only one frequency here. So we have a frequency of f naught, and at the frequency of f naught we have an amplitude which is a. So we get a very simple plot here, which is represented by a simple line, that we have a one single frequency f naught with an amplitude of a. Similarly, if we in order to complete the representation, we need to include the second piece of information, which is the phase information. So we are required to make another plot which is called phase, which is the phase versus frequency plot. In this plot, again we need to use the frequency as independent variable because we are trying to plot the spectrum. So independent variable will definitely be frequency, and the dependent variable is phase of the waveform, which is phi in this particular example. So if we plot it, we would see that the sinusoid contains only one frequency, which is f naught, and that one frequency has one phase associated with it, which is represented as phi. So there is only single frequency with phase phi. So these two plots, they actually show the complete picture in the frequency domain. One is the amplitude versus frequency plot, and second is the phase versus frequency plot. The first plot is named as amplitude spectrum because we are plotting amplitude as a function of frequency, so it will be called spectrum. And second is named as the phase spectrum because we are plotting phase with respect to the frequency. You can see that this a cos omega naught t plus phi is a sinusoidal function, which is a periodic function, and generally the periodic function has the plot which looks somewhat like this. It comprises of some specific number of lines, like this one contains only one line, but there may be other lines as well for different types of functions, but generally the periodic function has plot which appears as discrete lines. So this type of spectrum is named as a line spectrum. It's a line spectrum because we have discrete lines in the spectrum. Okay, so you can see that the same function which I showed in time domain, which is represented here, it can also be represented in frequency domain by these two plots, that is amplitude spectrum and phase spectrum. I want to emphasize that this curve and the previous curve, this one, they are representing the same function. They are not different functions, they are same functions. The only difference is the same function is plotted in time domain for this plot, and for this one the function is plotted in frequency domain. So these are two different perspectives of looking at the same function. So if we look this function from the time domain perspective, so we would see this type of variation here, and if we look at the same function with frequency domain perspective, so we would get these two curves which are amplitude and phase spectra. Okay, before continuing the discussion or taking other examples related to the line spectrum, let me summarize some basic conventions that we use to plot the line spectrum. So these are the commonly used conventions which we have taken as a standard while plotting the line spectrum. First of all, because we are plotting the spectrum, so the independent variable would be taken as frequency, cyclic frequency f. Typically we use calculate the cyclic frequency in hertz. So this is our independent variable, and if we want to identify some specific frequencies, so we generally use some subscript. For example, f naught represents a constant variable value. F1 would represent another constant value. So f with any subscript, they generally represent fixed values, whereas when we use simply f, so that means we are referring to the independent variable f. This convention is used in our textbook. However, I want to mention that some other books, they prefer to use radian frequency omega as independent variable instead of f. But we understand that omega and f, they are directly related to each other, so it does not make any difference whether you make a plot with respect to f or with respect to omega. However, in our case, we will be plotting all spectra with respect to the frequency variable f. Second important thing is related to the calculation of phase angle, because sinusoids can be represented in two ways, sine and cosine. So sine function and cosine function, both of them, they are sinusoids, and we know that sine and cosine, they differ with each other by a 90-degree phase difference. So in order to have a standardized representation, we need to use some standard or some specific reference to calculate the phase angle, and we have made the convention that we will always calculate phase angle with respect to the cosine wave. So always our reference point is taken as a cosine wave. So if in certain case we have a sine wave, so we need to convert that sine wave into cosine wave. And you may recall a simple mathematical relation that comes from trigonometry, that sine theta is equal to cos theta minus 90 degree. So if we have sine omega t, so we can convert it into cosine by using this standard identity from the trigonometry. Third important convention is related to the amplitude. Amplitude of any wave is always taken as a positive quantity, because amplitude represents the maximum value that wave can attain in frequency domain, in time domain. So this amplitude is actually taken as positive quantity only. If in any case we see a negative sign, so we generally attribute that negative sign with a phase change of 180 degree. So whenever we have a phase change of 180 degree, that means we will be getting a negative sign with the amplitude. So actually this negative sign does not come from the negative amplitude, rather it comes from the phase change. So whenever we see a negative sign, we need to absorb it into the phase to get a positive amplitude. So we have a standard trigonometric identity which is given here. If we have a minus a cosine omega t function with a negative amplitude, so this negative amplitude would be absorbed in the phase angle by using this relationship, that a cos omega t plus or minus 180 degree. It does not make any difference whether you are taking plus 180 degree or minus 180 degree, because we already know that both of them would result in a phase reversal, whether you take a phase shift of 180 degree or minus 180. So both are equivalent representation. So you can use any of these as per the convenience in the calculation. The fourth important convention is related to the units that we use in the phase angles. Generally the phase angles are expressed in degrees. So always whenever we talk about the phase angle, we represent the phase in degrees. However, you should note that other angles in the system, they are in radians. For example, omega t is also represent an angle, but this omega t angle is in radian. Of course, in the representation you would not feel any confusion in the calculation, because for degree we always use an appropriate degree symbol whenever we represent the angle in degrees. But you need to be careful in making your calculations, because we would be dealing with a mixed type of notation. Omega t is in radians, whereas the phase angle is given in degrees. So whenever you need to calculate, you either need to convert omega t into degrees or phase angle into radians, because before you add them together to get an overall angle. So this is a point of caution for you whenever you need to make any calculation. So after defining all these conventions, now we are ready to take up a simple example where we try to plot spectrum for rather complicated sinusoid or complicated periodic function. Actually, we are given a periodic function which is illustrated in this diagram here. So it's actually represented in time. You can see here is a time domain plot of the function, and it is periodic as apparent from the waveform. It's repeating after certain period. Actually, this function is mathematically represented by this function 7 minus 10 cos 40 pi t minus 60 degree plus 4 sin 120 pi t. So sum of these three terms is actually represented here as this waveform. what we want to do, we want to draw the spectrum of this waveform. So let us start plotting the spectrum for this particular type of waveform. First thing to note that we would be dealing with three terms or three sinusoids here because the overall waveform is represented as sum of three sinusoids. So we try to transform these sinusoids as per our convention. If you look at first term 7, it's a constant term, so for the time being I would leave it like this. The second term here actually it has a negative sign with the amplitude, and as per our convention we cannot allow a negative sign with the amplitude. So this negative sign need to be absorbed in the phase angle. So I would transform it into the phase angle by adding a phase difference of 180 degree. So this sign becomes a positive sign here, and we have added a phase difference of 180 degree. For the third term, you would see that this term is a sine term, and by convention we always calculate our phase angles with respect to cosine terms. So we need to transform this sine term into cosine term. So if we transform it to cosine, so we would be having a phase difference of 90 degree. So I have transformed this term into cosine. The first term 7 here, this 7 is actually a constant term. So constant term actually for voltage or current signals is actually representing a zero frequency term or a DC component in the waveform. So actually we have certain DC components. However, in order to make a consistent notation, we generally represent this constant term as a sinusoidal term with a zero frequency. So I can represent this this 7, this constant 7 as a sinusoidal function which has a zero frequency. So 2 pi into 0, 0 is actually the frequency, plus it does not have any phase, so it has a phase of 0 degree. Of course, eventually when you calculate this thing, so 0 plus 0 would become 0, and cos 0 is represented as 1, so you will end up with a constant number 7. However, this representation here makes it consistent with other terms. Similarly, for other terms, we have just simplified it. 10 cos this 40 pi t can be written as 2 pi into 20 because 40 pi is representation of omega. So this is omega, and we want to calculate frequency f. So I have written is 2 pi into in form of 2 pi into f. So 2 pi into 20, so we get the frequency f to be equal to 20, and the phase angle it calculates to plus 120 degree. Similarly, for the third term, this 120 pi t can be written as cos 2 pi into 60. So again we have the frequency 60 here in this representation. So now we have transformed the given waveform into our standard or conventional form. We can easily identify the frequencies as well as the corresponding amplitude and phases. So you can see that our waveform is represented as sum of three cosine terms, and for each term we have certain frequency and the corresponding amplitude and phase, which I have tabulated in this table here. So for the first term we have frequency of 0, and at 0 frequency you see that we have amplitude of 7, and the phase angle at 0 is actually 0 degree. For second term the frequency is 20, so the frequency is given as 20, and at 20 frequency you can see that the amplitude is 10 units, so 10 here, and the phase angle at the 20 frequency is 120 degree, so we have the phase angle of 120 degree. And third, we have the frequency of 60 here, and at frequency 60 we have amplitude of 4 units and the phase angle which is equal to minus 90 degree. At this point, I want to clarify that phase can take any value, positive or negative. Amplitude cannot take negative values, but phase can take negative values as well, like shown here in the third case, which has a negative value of minus 90 degrees. So after identifying each of the frequencies which are present in the signal and the amplitude, corresponding amplitude and phases, we are now ready to plot the spectrum. So independent function or independent variable in the spectrum would be the frequency. So I have taken the frequency onto the horizontal axis. So frequency represents the independent variable here, and we are using the amplitude, and you can see that from our signal we have three different frequencies, 0, 20 and 60. So we have 0 frequency signal at 20 frequency and 60 frequency. So we have three distinct frequencies here. At 0 frequency the amplitude is 7, at 20 frequency the amplitude is 10, and at 60 frequency the amplitude is 4. So at 0 we have plotted the amplitude of 7 units, at frequency of 20 we have plotted the amplitude of 10 units, and at the frequency of 60 Hertz we have plotted the amplitude of 4 units. So this completes our amplitude spectrum here. Similarly, if we try to plot the phase spectrum, again of the phase spectrum, the frequencies would remain the same. We have 0 frequency, we have 20 Hertz frequency and 60 Hertz frequency, and the corresponding amplitudes are tabulated here. You can see that at 0 frequency the phase angle is also 0, at frequency of 20 Hertz the phase angle is 120 degree, and at 60 Hertz frequency the phase angle is minus 90 degree. And I have plotted here at 0, you can see that the phase is also 0, so we are dot here. At 20 Hertz frequency we have a phase angle of 120 degree, so we see a line which corresponds to the phase angle of 120 degree, and at 60 Hertz we have a phase angle of minus 90 degree, so we have a downward line here to show that we have a phase of minus 90 degree at 60 Hertz frequency. So this gives you the phase spectrum for the sinusoid shown given in the problem. At this stage I want to mention one more thing. You can see that the overall spectrum it was a periodic function. The overall spectrum appears in form of lines. So we see 3 lines in the amplitude spectrum here, and we see 3 lines for the phase spectrum here. So generally the spectrum is that appears as a lines. It's named as line spectrum. And you must know that all the periodic functions, whenever we plot their spectra, so their spectrum generally appears to be line spectrum. Second important thing is that this spectrum is actually called a one-sided, or sometimes we call it a single-sided spectrum, or a positive frequency spectrum. You can see that the frequency line starts from 0 here and goes up to infinity. The frequency variable takes the values from 0 to infinity. So that positive frequencies only, it actually represents a single-sided spectrum. There is another type of spectrum that we will be discussing later in this week, which is named as two-sided or double-sided spectrum. What is two-sided spectrum? It actually involves some negative frequencies. At this point I just want to mention that we have another type of spectrum that involves negative frequency. How we plot that we will be discussing later in this week, inshallah. Okay, so this concludes our discussion how we can draw a single-sided line spectrum for a periodic function, and how we can represent a signal in the frequency domain. There is another representation which is sometimes used in analysis. That representation is called Phasor representation. The Phasor representation comes from the Euler's identity. We know that e raised to power j theta, it can be represented as cos theta plus j sin theta. If you have e raised to power minus j theta, in that case it will be represented as cos theta minus j sin theta, where j is mathematically is equal to under root of -1 and theta is some arbitrary angle. And from our point of view, you can see that j corresponds to a phase difference of 90 degrees. So if we take a look at this Euler's identity, we see that the cosine function is actually a real part of this e raised to power j theta. So I can write cos theta to be equal to real part of this e raised to power j theta. And if we represent the generalized form of a cosine function, which is shown here, and we have previously discussed as well, with some amplitude and frequency and phase, so we have a function a cos omega naught t plus phi. So I can write it to be equal to a cosine of a real part of e raised to power j omega naught t plus phi. And I can separate out different terms here. So e raised to power j phi can be written separately, and e raised to power j omega naught t can be written separately, and we have an amplitude a, which is constant number. This representation is actually named as Phasor representation, and you can see that this representation contains all three important information that are related to the representation of sinusoidal function. That is, it has amplitude, it has some phase, and it has the frequency, which is here as well. So these three three parameters are combined in this Phasor representation. And if we try to plot this phasor, so this phasor is plotted as a vector in a complex plane. A complex plane has a real axis and imaginary axis, and we can plot it in the complex plane. So let me show the plot here. So this is the plot of the phasor. So the same phasor is represented as the vector in the complex plane, where the real axis corresponds to the cosine and imaginary axis corresponds to the sine. You can see from this Euler's identity here, the cosine function forms the real part, and sine function it forms the imaginary part. So the real axis is here, and we have a phasor which has an amplitude of a. So as a vector, it is represented as the length of the vector. So that the length of the vector is actually equal to the amplitude of the wave, and it has a certain phase which is measured with respect to cosine function, that is, it is measured with respect to the real axis as here. So if you look at t equal to 0, in that case the phase angle will be angle of this vector from the real axis. And if you plot the projection of this vector onto the real axis, so you will get the actual sinusoid, which is a cos omega naught t plus phi. So always the real axis projection gives you the cosine component. You can also calculate the sine component by making a projection on the imaginary axis, but for the time being we are discussing the real axis only. Since we have third information, which is f naught, which is the frequency of revolutions per second, so we take this frequency to be a rotating phasor. So this phasor is actually rotating with a frequency of f naught. So we have represented the arrow here that this phasor is not a constant phasor, is actually changing with respect to time, and the rotational frequency is represented by frequency of the wave, which is f naught. You can see that this phasor representation has all three parameters that are needed to completely specify the phasor, which are amplitude, phase angle, and rotational frequency. The amplitude is represented by the length of this vector, the phase angle is represented by this angle from the real axis, and the rotational frequency is generally represented by arrow that it's rotating in the counterclockwise direction with a certain frequency. So this is another representation which is actually, if you look at here, you would see that it's actually a complex domain representation, which is sometimes very helpful in analysis as well. So far we have talked about two important aspects regarding signal representation. One is the frequency domain representation of a periodic function. So far we have only discussed the one-sided spectrum, but in our next lecture, inshallah, we will be talking about the two-sided spectrum as well. And the second representation that we use to represent the sinusoids in the sinusoids is a phasor representation, where the sinusoid is represented as a vector in the complex plane. So this sinusoid has been represented as a vector in complex plane, so it makes the solution convenient by treating them as a vector, and different sinusoids can be analyzed by using the vector analysis. So I conclude the discussion for this lecture at this stage. We will be discussing the double-sided spectrum in our next lecture, inshallah. So thank you all.